Hello. The purpose of this video is to review limiting reactant stoichiometry problems. In a limiting reactant stoichiometry problem, you are given a balanced chemical equation and you are told the initial masses of both reactants. And you are asked to answer the following questions. Number one, of the two reactants, which one is limiting and which one is present in excess? Number two, what's the theoretical yield of product? That is, what is the maximum mass of product that you expect to get? And finally, what mass of the excess reactant is left over after the reaction is finished? I've taught you two ways to solve these problems. I call them the have and need table method and the calculate the theoretical yield twice methods. So I'd like to go through a problem illustrating both of these two methods. Aqueous solutions of iron 3 chloride and potassium carbonate are combined, forming a precipitate of iron 3 carbonate, while potassium chloride remains in solution. On a test or quiz, I would normally ask you to write and balance the equation. I'll do that for you now in the interest of time. But the problem is as follows. If I combine 10.00 grams of iron 3 chloride and 15.00 grams of potassium carbonate, which reactant is limiting and which is present in excess? What's the theoretical yield of precipitate of the iron 3 carbonate? And finally, what mass of excess reactant is left over? Here is the balanced equation for simplicity. And to make things easier, I've even calculated the molar masses, which we'll use for the problems. So let's look at this problem using both of the methods. First, the have and need table. I'll begin by taking the mass of each reactant I'm starting with and simply divide by the molar masses to convert to moles. I can't do anything with masses, I've simply got to turn the masses into moles. So I'll take my 10.00 grams of iron 3 chloride, divide by the molar mass 162.20 grams per mole, to give me 0.06165 moles of iron 3 carbonate. Likewise, I'll take my 15.00 grams of potassium carbonate, iron 3 chloride, not carbonate. I'll take my 15.00 grams of potassium carbonate, divide by its molar mass, 138.21 grams per mole, to give me 0.1085 moles of potassium carbonate. These are the amounts of each reactant that I have. That's what I'm starting with. That's what's actually present. To figure out which is limiting, I will multiply each of these by the appropriate mole ratio to figure out how much of the other reactant I need. So I'll take my moles of iron 3 chloride and multiply by the mole ratio 3 moles of potassium carbonate needed for every 2 moles of iron 3 chloride I have, to give me 0.09248 moles of potassium carbonate needed. I'll do the same thing with the moles of potassium carbonate I have, but I'll multiply by the inverse of the mole ratio, 2 moles of iron 3 chloride needed for every 3 moles of potassium carbonate I have, to give me 0.07235 moles of iron 3 chloride needed. Okay, so that's my need column, if you will. And now I compare what I have to what I need. I would need 0.09248 moles of potassium carbonate to use up all of the iron 3 chloride. I have more. I have 0.1085 moles of potassium carbonate. So that tells me that potassium carbonate is present in excess. Let's just confirm. I need 0.07235 moles of iron 3 chloride to use up all the potassium carbonate, but I only have 0.06165 moles of iron 3 chloride. Okay? So I can say I don't have that. So that tells me that iron 3 chloride is my limiting reactant. So I will immediately draw a box around the moles of limiting reactant that I actually have and write LR next to it to tell me that that's limiting reactant. Okay? So I've answered the first question. Comparing the amounts that I need to the amounts that I have, I can conclude that iron 3 chloride is a limiting reactant. Now that I've done that, I use the moles of limiting reactant I have to calculate the theoretical yield of product. So I'll take my 0.06165, there it is, moles of iron 3 chloride I have, multiply by the appropriate mole ratio, which is 1 mole of iron 3 carbonate for every 2 moles of iron 3 chloride. And then multiply that by the molar mass of iron 3 carbonate, 291.73 grams per mole, to give me my theoretical yield, which is 8.993 grams of iron 3 carbonate. Put a box around that, and that is my theoretical yield. The final question is, how much of the excess reactant is left over? Well, we know that potassium carbonate is present in excess. There's the amount that we start with. There's the amount that actually reacted. So to figure out how much is left over, I simply subtract one from the other. So 0.1085 moles of potassium carbonate that I originally had, minus the 0.09248 moles of potassium carbonate that reacted, gives me 0.0160 moles of potassium carbonate left, and then I'll simply convert that to mass by multiplying by the molar mass. 0.0160 moles of potassium carbonate times its molar mass, 138.21 grams per mole, gives me 2.21 grams of potassium carbonate left. That, in a nutshell, is the have and need column method of solving this problem. In the next video cast, I will show you the calculate the theoretical yield twice process.